Good afternoon, everyone. My name is Jitka Metelkova, and I'm going to show you some of my work on the elevated edges of parts made by laser powder bed fusion. And as was told, I did this work at KU Leuven in Belgium. Yes, sorry. So after a very short introduction of the problematics, I will explain a little bit more about the method I use to characterize these elevated edges, and then some of the results some of the observations we made based on or after multiple laser exposure of the surface, also called laser remelting. So how this laser remelting is actually influencing these elevated edges. And the ultimate goal of this was also to proceed to post-processing with a laser ablation process, but we will go through it step by step. So for horizontal upfacing surfaces, there are two main issues. One of them is low surface quality. That, I guess, is a topic that is going to be discussed further in this conference. So all these scatters, ripples on the surface, or insufficient connection between the tracks. But the topic of this speech is about the edge effect, these build-up edges that can occur during the selective laser melting process. Okay. So the goal of, as I was saying, the goal of the characterization of these edges is not only to have an idea how these edges look like and why, possibly, but also to be able to afterwards proceed to post-process correction that can be also done in process, and to increase the quality or the dimensional accuracy of the part. But actually this additive characterization is quite a tricky thing, because you have to ask yourself, what is the measurement tool I should use and how should I characterize it? So I will try to answer these two questions. So first of all, the measurement tool, should you use an optical microscope, a CT, or maybe tactile profilometer? Well, with an optical microscope, you often encounter this kind of problem, that for quite horizontal surfaces, you have a data coverage that is relatively sufficient. However, for steep angles, such as these edges, you can see that there is almost no data. So after interpolation, of course, you will get some guess from the algorithm of where the surface probably is. But for example, the edge end, the limit, it's pretty much a wild guess. So this might not be the best solution. A CT scan is possible, but of course you have to have the equipment available with the right person that knows how to operate a CT scan. And also the samples can be only small, because big samples are a bit tricky with a CT scan. And besides this, all the scaling problems and so on, I guess some of my colleagues will probably talk about it. So this was not a suitable solution for our case. So then actually we ended up with a tactile profilometer equipped with a Y stage, motorized Y stage that we could use for the analysis of these elevated edges. So we were going across the specimen surface, and then the probe was landing on a gauge log that was positioned about 1 millimeter below, so there was no risk of damage of the profilometer. And this way, we made 150 profiles with a 20 micron spacing, which gave us a length of the edge that was sufficient for stable results. So this way, I showed you the method that we choose for it, but how were we going to characterize the edge? So first of all, you have to consider that every time the probe touches, makes the contact with the surface, and gets over the edge. So every time the zero, so the height coordinates are different. So in the end, you end up with quite a flat beginning of all the profiles, but very wavy surface that is actually flat because we are landing on a gauge block. So this is the first step that we have to correct. And then after this, we are correcting the slope of the main surface. However, the question still remains, where does the edge end? Because we cannot consider it as the edge in the classical sense, where we are based on contrast, we detect the edge, because we are here talking about the 2.5D data, so profile measurements assembled together. So what we, in the end, what we considered as the edge limit is actually the point where the probe is not in the contact with the material anymore, but starts to slide on its length. So therefore, we can consider the change of the slope that can be then detected through the first and second derivatives. So the downward peak of the second derivative. But if we have a look at the real data, you can see that the first derivative there can be about the same zone can be detected as what we expected. However, the second derivative, there was a lot of noise, so it was not possible to detect this downward peak. Therefore, we proceeded to smoothing first of the first derivative, and then it was possible to detect this downward peak to detect the outer limit of the edge. So then we could project these edges, these limits of the edge on our 2.5D measurement, and correct for the positioning error actually. And how we checked that what we actually are measuring is good enough for our needs is that we took a part with a laser ablated zone, as you can see there, with an approximate width of 491 microns. And then on the middle zone, we proceeded to this kind of measurement. And there we could then distinguish the start of the laser ablating zone and the end, the detected edge limit, which was pretty close to our needs because our edge is in the order of 400, 500 microns wide. So this is the precision that was sufficient for our needs, actually. So therefore, we could proceed to mean edge profile generation. You can see all the individual profiles, and in fact, the mean profile with the standard deviation that can be then assessed. So we decided to assess in the beginning 3 basic parameters, which is the maximum height, then the edge length, and the edge volume. So now the question is, how does the number of remelting passes and the rotation angle between the remelting passes, how does it influence the edge morphology? What do I mean by the rotation angle? I mean whether the scan vectors are parallel or with a 90 degrees rotation or 120 degrees rotation. So first, if we have a look at the maximum height, we can see that after the first remelting pass, the maximum height increases from 75 to 100 micrometers, and then it starts to decrease till about 70 micrometers. The rotation angle doesn't seem to have any significant difference, so it seems to be more the number of remelting passes and not the rotation angle. Then, if we have a look at the edge length, we can clearly see that the edge length is increasing after the first remelting pass and keeps increasing till the 10th remelting pass. And concerning the edge volume, it increases after the first one, but then stays about constant or only very slightly increasing. So in the end, what does it all mean? If we have a look at the measurements itself, you can see here the 2.5D data. So this is the part as built, so we can see a number of spatters on the surface that we want to get rid of by the multiple laser exposure. You can also see that the edge is quite irregular. Its variation is quite important. After the first remelting pass, you can see that the height went up, but also it's more regular than after the as-built state. And the length of the edge is then increasing with the increasing number of remelting passes, and the height is decreasing. And if we have a look at the metallographic cross-section, you can see this is the as-built state, so quite a sharp edge at the end. And this is the shape after the 10 times remelting. And if we compare this to the mean profile that we have generated, you can see that the shapes are actually quite closely matching. So you can observe that the main volume is shifting from the edge only a bit towards the central part of the part. And what can be the possible explanations? So first of all, you have to consider that you are not polishing, laser polishing with no influence of powder, because you are still surrounded by the powder. When you're building, usually you first scan the contour vector so that you have a better side surface. But during that scanning of the first vector, you have actually powder supply for both sides. So this is the reason why even in the as-built state, it can lead to elevated edges, because you have double the supply of powder that you can put in your melt pool. So then you scan for the building, and then after building, if you do this multiple exposure, you can actually slightly overheat your surface. And by the slight overheating, it is possible there is some degree of evaporation of material, so that the surface, middle surface, can lower a little bit. And also by overheating or heating more, you can bring a little bit more powder inside the edges, so you can contribute to their buildup. And last but not least, you're also moving around the material, so you're by remelting, you're pushing the material in and out and in and out, so that by this you also increase this phenomenon of increased edges. And so I just want to point out that I was using exactly the same power, speed, and head spacing parameters as for the substrate, because this way you have only these elevated edges. But in case you have much higher heat input, you can see that actually the melt pool can lead to much larger melt pool, so that it can even overflood outside the part. So this is definitely not something that you want. So you have to account for this, and you have to change your process parameter or the offsets so that you avoid this. So this is not the case I was showing you, but it can happen. And the last part concerns the post-process correction. So you can see that this way, from this quite high height of the edges, we could reduce the height to close to the middle plane. However, if you have some larger particle accumulations there, of course, if you use, in our case, we use the femtosecond laser ablation, and this is a cold process, so there's no melting. So, of course, you will still have this high deviation around the edges in case you have this kind of features. However, we could reduce the maximum height quite significantly. Of course, it could be reduced even higher, but by then the method was not fully developed, so it can be even closer to the zero line. So as my conclusions, I have just shown you a way how to characterize the edges by a tactile performometer. We saw that the edge morphology is changing mostly with the number of remelting passes and much less with the rotation increment angle between the passes. However, the scanning parameters, the power, head spacing, and so on are very important, so it has to be also taken into account if you're doing surface remelting. And I show you a way how to post-process these edges to have a higher dimensional accuracy at the end. And as a last word, we have developed a machine that can do this also in situ, so we can also in situ correct edges or other imprecisions or create new features. So thank you for your attention. If you have any questions, I'm
Thank you very much for the really interesting presentation. There is time for a couple of questions. Any question? Well, I have a couple of questions. So the first one is about your measurements. So you are evaluating some dimensional characteristics of the elevated edge, right? Like the height, for example. But this measurement is important also for the post-processing operation that you need to perform later. So my question is, are you planning or did you already determine the uncertainty of this measurement? So you can have, yeah, you can be sure about your post-processing operation. So the uncertainty of this height measurement, for example.
So what I did not show here, but it's included in the paper, we did edge variation. So basically we measured the edge at 3 different locations and also the full edge. And then I compared the results between these different variations, between these different locations, but they were done by the same method. And they led to quite an acceptable variation of these parameters, if this answers to your question.
Because, for example, I saw that you were using also a gauge block, which was like a reference for the height.
Yeah.
Maybe, yeah.
So first we measured the gauge block, of course, to be sure that it's flat and there are no, it's not damaged or something. So it was within, I don't remember the value, but it was very, very low. It's in my head. Sorry.
Okay, maybe we will discuss there. And there is another question. Okay.
So it's related to the question of measuring uncertainty. So when you measure over an edge with a contact system, at that point the effect of the stylus radius will be large. So on this one method you can use to measure a stylus radius. So did you apply any mathematical correction to take out the effect of the tips of the tip?
No.
Understand that effect on the uncertainty of the edge.
No, I did not consider the tip in my analysis.
It's quite simple to do. You can some code to do that.
Yeah.
Okay, there is another question, right?
One of the concerns with laser remelting for elevated regions is the additional time to the processing. But what might you say would be the relative additional time between the processing laser or the femto laser method that you were showing? Is one quicker than the other, or?
Between the processing laser and, sorry?
Well, first of all, you use the processing laser to reduce the elevated region and a femtosecond pulse laser, right?
Yeah, the femtosecond pulse laser, it was ex situ, it was post-process, so it was, you have quite some positioning on the stage because, it takes some time to set up. But the idea is that now we have also in situ, so we have it's not a femtosecond, it's a nanosecond laser that we have in our machine, so that there, I did not quantify yet the additional time, and it also, of course, depends on the requirements, if it's how important it is to have it perfectly flat. But it's, it was a matter of maybe 30 seconds or 1 minute for these 3 or 4 millimeters. So in this order of magnitude, I did not quantify yet. If it's
And there are how many layers are going through the remetting process? Not just the first last layer, right? Maybe before last layer, the several layer will be coming through the
the remelting we did only on the last layer.
Only last layer.
Yes.
Yeah, I know from other link, like for example, US, or Thailand, I use, after the last 3 years, they stop using the remetting force. Maybe they have a different effect on the age.
Yeah.
Okay.
So we can thank the speaker again because we are out of time. So thank you very much for the talk.